Hello everyone, I am Mukesh from Raman Research Institute, and today I'll be talking about our recent work, Misty, Patchy and Turbulent, Constraining the Cool Circumgalactic Medium with MCC. So what is CGM or the circumgalactic medium? The galaxies are surrounded by this vast reservoir of gas, which we call as a circumgalactic medium. It is important to study CGM in order to understand galaxy evolution because it contains the accreted gas from the intergalactic medium, which is a fuel for the star formation. The intergalactic medium is the space between the two galaxies. The CGM also contains the outflowing gas which is ejected from the stellar activities or the supermassive black hole activity. The gas in the CGM is multiphase with temperature ranging from 10 power 4 to 10 power 7 Kelvin and is also very diffuse gas with number density varying from 10 power minus 4 to 10 power minus 1 particle per cc. In this work, we will be talking about the cool gas, which is around 10,000 Kelvin, but there are other gaseous phases as well, like the warm or the virial phase. So how do we detect this gas in the CGM? The routine way to detect this gas is using the absorption line spectroscopy. For that, we need a background source, which is typically a quasar. The light distribution from this quasar looks like this as a function of frequency. When the photons from this quasar passes through the CGM of intervening galaxy, the ions which traces the cool gas like magnesium 2, carbon 4, iron 2 will absorb the photon of a specific frequency or the wavelength. And when we look at the spectra from this quasar reprocessed by this CGM, it looks like this. So there is an absorption in the continuum of this source. So the primary observable from this absorption line is the equivalent width, which is the area within this absorption profile. But the other important quantity is the column density, which is the line of sight integral of the ionic number density. Larger the column density essentially means larger the number of absorbers. From the observation, equivalent width is converted into column density using the Voigt profile modeling or the other methods. So from the observations, we have the column density. So in this plot, I am showing the magnesium 2 column density as a function of distance from the galactic center normalized by the virial radius of the CGM for the cos-halo survey. COS means the cosmic origin spectrograph. It is an spectrograph on the Hubble Space Telescope, and this is one of the survey using this instrument. So here we can see detections along with the upper and the lower limits. And also we see a large variation in the column density at similar impact parameters. So how do we understand this observation? So here is our model. We propose that the cool gas does not fill the entire CGM volume. Rather, it resides in these clumpy structures, which we call as the cloud complexes. This plot shows the line of sight projected distribution or the 2D distribution of the cloud complexes in the CGM. So what is the consequence of this distribution and how it helps us to understand the observation better? So let us focus on this dotted black line, which is at a distance of 100 kiloparsec from the galactic center. So the line of sight passing through these empty regions will result in the upper limit, which is basically these points. The line of sight passing through one or two or fewer cloud complexes will result in detection. And the line of sight passing through these multiple cloud complexes will result in the lower limit, which essentially means larger column density. So this basic model explains this large scatter in column density at very similar impact parameters. And this is the main point of this paper. So for more detailed analysis and detailed work, please visit our paper, which is on the archive. Thank you.